So we're moving on to inverse trigonometric functions. And so I just want to remind you a bit about inverse functions in general. So let's just pick a simple example, y equals 2x plus 1. And functions like this are designed for you to plug in x, right? So we would say something like, hey, x equals 3, and then we would calculate y by just doing arithmetic. 2 times 3 plus 1 is 7. Now an inverse function goes the other way. An inverse function would say, okay, we want to start with y. So maybe I have something like y equals 9, and I want to know what x equals. Now in this case, I have to solve this equation. And so I would subtract the 1, which gives me an 8, and then I would divide by 2, and that gives me x is 4. And every time I'm given a y, I would have to then solve. So what we do with an inverse function is we just solve with x and y up front, so then we can just plug in and get the answer from an inverse function. So then we're going to say that f of x equals 2x plus 1. We want to know what the inverse function is, which is written with a little -1 up here. And that's not reciprocal. It's not -1 power. That's inverse function. And again, that is not the power -1. To calculate an inverse function, the procedure is to switch y with x and then solve for y. So kind of like that solving procedure, but I would do step 1, I would say x equals 2y plus 1, and then solving that, I would subtract 1 over, and then I would divide by 2. So I could say y equals x minus 1 over 2. So that would be the inverse function. So then I would claim if f of x is equal to 2x plus 1, then the inverse of f is equal to x minus 1 over 2. Now we could write that a different way, but I'm just going to leave it that way, just to get to the idea of inverse operation. So the opposite of addition is subtraction. The opposite of multiplication is division, and the inverse function has that. The other thing about inverse functions and solving equations is you do the math in the opposite order. The arithmetic of this function says to multiply and then add, and the inverse function should reverse that. It should first subtract and then divide. So that's the idea of an inverse function. And sometimes inverse functions are easy to find. Sometimes they're hard to find. It kind of depends. Another way to think about inverse functions is just the idea of switching y with x. Right, that was that first step in the procedure for calculating the formula. So if we had a function with a table of values, x, y, so this is f of x here, and I knew that, say, if x was 0, y was 1, and if x was, let's see, 3, y was 7, and if x was 4, y was 9, then the inverse function for x and y, we just switch that table for f inverse. So then I would have to point, instead of 0, 1, I would have to point 1, 0. Instead of 3, 7, I would have to point 7, 3. Instead of 4, 9, I would have to point 9, 4. And notation-wise, the idea of an inverse function is it undoes what the function does. So if we started off with some x value, and then we apply f to it, that means we just calculated the y value. And then if we go and on top of that, we apply the inverse function to all of that, that should undo, because the inverse function takes y and changes it back to x. right? So this is another kind of definition of what it means to be an inverse, that they undo each other and give you x back. And the order of operations shouldn't matter. If we did f inverse on some number first, and then applied the original function on top of that, we should get x back no matter what. Let's test that with the function we were just working with. So we a moment ago had f of x equals 2x plus 1, and we calculated that f inverse of x was equal to x minus 1 over 2. So I'm going to do this first version here. I want to calculate what is f inverse of f of x. Safe way to do that is to write f inverse down with parentheses instead of an x. That would be parentheses minus 1 over 2. What goes in that parentheses is whatever f of x is. Let's use red. F of x is 2x plus 1. So that means I drop a 2x plus 1 here and then clean it up. Well, there's not much going on with the parentheses, so I can subtract the 1. 1 minus 1 is 0, so that just leaves 2x on the top divided by 2, which gives me the x that I wanted, right? So I'm checking to see if this is really the appropriate inverse function. And I know a function is an inverse of another if when I compose them, I get x. So note, composing a function with its inverse simplifies to x. Doesn't matter the order of the composition. So that's important too. Other inverses you've seen before, if we said that f of x was equal to the square root of x, then f inverse of x would be equal to x squared, sort of. The square root of x, you might recall, is half of a sideways parabola. So that means I only want half of this. So with this function here, we have a domain of x is greater than or equal to 0 and a range. Remember, the domains, the x values you get to play with, range is the y values. Y is greater than or equal to 0. And again, we switch x with y, and the domain and range are pretty much the same numbers, just one's for x and one's for y. That means I can only claim this is the inverse function if x is greater than or equal to 0. So I only consider half of that function there. Alternatively, if I were looking at the function negative square root of x, that would be a vertical flip. So that would be this guy right here. That means the inverse, I want the other half of this parabola. So then the inverse function would be x squared, but only if x is less than or equal to 0. Right? So if I were to graph that inverse function over here, the inverse function, let's maybe do that in green or blue. The inverse function would be this one right here. So this is f inverse, and the red one is f of x. If I do that up here, this green one is f of x, do the inverse in blue, or maybe red to stand out, would be this right here. Now this brings me to another cute property of inverse functions, and that is graphically a function and its inverse are symmetric about the line y equals x. So I'm going to draw the line y equals x in here. Ooh, that was not a straight line. Let's try that again. There we go. Now, if I drew my graphs neatly, that would be perfectly symmetric on each side. And here, oops, if I drew my graph neatly, let's try that again. Come on, there you go. I should find that around the line y equals x, those are perfectly symmetric. And so sometimes a graphing utility is better because it's a little neater if it's graph. So another property of inverse functions graphs of a function and its inverse function are symmetric about y equals x. So I was just hoping with all of this to jog your memory on what it means to be an inverse function. How do we get inverse function? What are their properties? All right, so one more thing about a function, it's inverse. For a function to have a proper inverse, then we need to have the function be what's called one-to-one. So that means a function means that every y value goes with every x value goes with a single y value or no more than one y value. For one-to-one, we want to be able to reverse that idea. So let's look at one-to-one. Again, this should be review. So a one-to-one function means each y value, it's supposed to be each there, let's try that again, corresponds to no more than one x value. And a common place where that constraint fails at first is just your basic parabola. So if we were to graph y equals x squared, right, it's this U-shaped curve. And if I pick some y value here, that y value can be traced back to this x value here and to this x value here. So for example, if y were 9, I would find x equals -3 leads to 9 or x equals +3. So that means this function's not one-to-one. Sometimes we just abbreviate it as 1-1. So to make a function one-to-one, we basically need to eliminate, kind of erase part of the graph till we get it to be one-to-one. So I have two options here for doing that. I could say, well, let's just eliminate that side of the graph, would be one option. And now this side is one-to-one. Or I could say, well, let's eliminate this side of the graph. And then that side would be one-to-one. So I can take it either way, kind of depends. And if you look back here, right, you could see that in this case, I kept the right side, but in this case, I kept the left side. And sometimes it's a decision that's based on the original function. Sometimes it's a decision that's just arbitrary and you just got to make it based on the situation. So let's look at a graphing utility for a minute for that. Desmos will do nicely. Let's get rid of that one. And so again, if I just consider y equals x squared here, right, it's clearly not one-to-one. The inverse function, one way to write it would be x equals y squared. And I'm kind of lying when I say function because that ain't a function, right? It fails the vertical line test. So it is an inverse relation between x and y, but it's not a function because it fails the vertical line test. For that to be a function, I have to erase the top part of that parabola or the bottom part of the parabola, depending on what I want to do with the original one. So here comes our next big challenge. So again, that's a decision that has to be made, and it's either arbitrary or you have a reason to make it. Now consider something like y equals the sine of x. When I try to think about it, whether a function's one-to-one, I imagine drawing a horizontal line and seeing if it hits the function more than once. If any horizontal line hits only once, it's one-to-one, and I can easily identify the inverse. If it hits more than once, then it's not one-to-one, and I got to figure out what to erase. And so you can easily see that if I graph the line y equals 1/2, that hits this curve many, many times. How many times? Well, infinitely many. Just keeps going and going and going. So that's a problem. If I just graph the inverse relation, that would be x equals the sine of y. you can see that that definitely ain't a function, right? It's a vertical line test, it fails for lots of vertical lines, right? Any vertical line, x equals -1 to x equals 1 is a problem here for this. So that is not a relation. So I got to figure out what part of the sine to erase to get an inverse function so that the inverse passes the vertical line test. So let's draw that on a piece of paper. So let's make a sketch of y equals the sine of x, showing a couple of periods. So remember, the sine of x starts at the origin, goes up, down, back up, right? And then it just keeps repeating that pattern. Up, down, back up. And it repeats that every 2 pi. Goes the other way too, right? Other way it would go down, up, and down. And so that would be -2 pi over there. And this clearly is not a function. So what I want to do is redraw it and then erase some of it. Sorry, it's not 1-to-1. I want to erase part of it until it is 1-to-1, until it passes the horizontal line test. Okay, so let's make a note of what we're going to do. Erase part of graph until it is 1-to-1, that is, passes the horizontal line test. And like the vertical line test for a function, a graph is a function, if any vertical line hits no more than once, horizontal line test means any horizontal line hits no more than once. So I'm going to make a copy of this and redraw it or erase it. So let's grab U. And then start erasing. Okay, so I kind of like having this point at the origin here. So if I were just to start erasing, like maybe up to there, I can't just keep this hump because it would fail the horizontal line test. So that's a problem. So thinking about this graph, once it starts to turn, I have a problem. So basically I want to cut it off here and then get rid of that. And you'd say, well, you know, it'd be nice to keep a whole period, but the problem with that, right, is in a whole period, it keeps cutting back on itself vertically, and it's going to fail the horizontal line test. So over here, once it starts heading back down, I can't have that. It's going to fail the horizontal line test. So I got to go basically to the peak here, and I got to cut it off. Otherwise, if I try to keep any more of the graph, so again, for the inverse, I want to keep as much of the graph as I can, but I want to have it pass the horizontal line test. So let's put a horizontal line in here, green one, and let's start with it up here. And again, the problem with the original function is any horizontal line between y equals -1, come on, there you go, between y equals 1 and -1, this thing fails for it, hits way more than once, hits infinitely many times. So back down here, right, the problem is once it goes past that peak, I'm going to fail the horizontal line test all through here. Once it goes past that bottom, I'm going to fail unless I erase from that bottom point. So what did I end up with here? Let's take a look. So this is 2 pi, in the middle here is pi, and then in between 0 and pi is pi over 2. And we know at 90 degrees or pi over 2, the sine reaches its maximum of 1. So what I've done in this new version of the graph of the sine is I said, okay, you got to stop right there at pi over 2. Can't go any farther. That means your peak is at 1. Same thing on this side. I said stop at -pi over 2. And that means you bottom out here at -1. So now I have this new function right here. I'm going to call that function f of x. And f of x is equal to the sine of x only if x is between pi over 2 and -pi over 2. right? And that was supposed to be a less than or equal to there. It's a little messy. Let's clean up those guys. And so now, and actually maybe we'll make some dots there to indicate clear stoppage, and we include those endpoints. They're part of it. Notice the less than or equal to. If I make a table of numbers with special angles to go with that, then what I'm saying here is, let's see, we got x versus f of x, starting at negative pi over 2. And I'm keeping all the way up to pi. Special angles in between would be like negative pi over 3, 3, there we go, negative pi over 4, negative pi over 6, 0, pi over 6, pi over 4, and pi over 2. And again, there's lots of points in between those. Those are just the special ones. And the y values there would be negative 1, negative square root of 3 over 2, negative square root of 2 over 2, 2, negative 1/2, 0, 1/2, square root of 2 over 2. Let's say I missed something there. I missed my pi over 3. Let's make that pi over 3 and then pi over 2. Square root of 3 over 2 and 1. So this is the function I'm keeping. And again, this is important. I have a new domain here. All right, so that's my domain. These are a selected few numbers from my domain. Special angles. And notice the corresponding range is pretty much the same range the sine had before, which was from -1 to 1. So that's kind of cool, same range. Which is y is from -1 to 1. Now the inverse function basically just flip-flops that stuff. So if I make some notes about the inverse down here, what's the inverse function going to look like? So I'm going to have an inverse function, f inverse, right? It's the inverse of the sine. We usually call the sine inverse. It's also called the ArcSine. And most computers recognize the phrase ArcSine, just like most computers recognize SIN as the sine. And its table of values basically flips this table of values. So x, f inverse of x, instead of having the point negative pi over 2, -1, it would have the point -1, negative pi over 2. Now, I'm not going to do all of these, I'll just do a few. Instead of the point negative pi over 3, square root of 3 over 2, it would have the point negative square root of 3 over 2, negative pi over 3. Instead of the point pi over 6, 1/2, it would have the point 1/2 pi over 6. Instead of the point, say, pi over 2, 1, it would have the point 1 pi over 2. As far as its domain, we just switch x with y. So the domain would be then x values that are between -1 and 1. Oops, I drew that on the wrong side. And the range of this inverse function would be what was the domain of the original function. So that would be negative pi over 2 to pi over 2. Let's make a quick graph of this and we'll ask a computer to graph it for us to compare. So new page. If f of x equals the sine of x, then the inverse function, I'm going to call the ArcSine of x. And its graph, we can reproduce. Let's get a better line. Its graph is going to have a domain from -1 to 1. So let's say here's -1 there. And here would be about 1 there. Pi is about 3, so pi over 2 would be about 1.5. So if I was going to draw this to scale, If 1 is about here, 1.5 would be about here. So pi over 2 would be a little bit higher, be about there. -1, negative pi over 2 would be about there. And what do I know about this function? Well, I just flip this table of numbers. So it's going to have the point -1, negative pi over 2. So -1, negative pi over 2 down here. It's going to have the point 0, 0, just like the original function. That's nice. And then it's going to have the point 1 pi over 2. And then it's going to increase over to that there, and it's going to decrease down to that there. And how do I know it's arcing in this direction? Well, I know it's arcing in that direction just by thinking about that y equals x idea. So if the original sine function, so again, this is supposed to be y equals x. If the original sine function did something like that, then the inverse would have to do something like that because they have to be symmetric. So it's got to arc in that way right there. So this is the graph right there, to the best of my artistic ability, of y equals the ArcSine. Often instead of ArcSine, you will see Sine Inverse, which would be written like that. So that means Sine Inverse. It is not 1 over the sine. 1 over the sine is the cosecant, and that graph right there ain't the cosecant. You with me? All right, let's graph this on a computer. So y equals, and some computers it's ArcSine, some it's ASine, and I can't remember what Desmos does. I'm going to try typing ArcSine. Hey, it liked it, of x, and there it is. There's my cute little wave there, but only part of it. And if I put in there the line y equals x, I can see that the purple chunk up unto its max and its min is symmetric around the line y equals x to my new red inverse function here, right? So can we highlight that one? There we go. So inverse sine. So we just had a big overview of what is an inverse function. The inverse sine, which is better named as the ArcSine. I'll explain why we're going to call it the ArcSine in a minute. And now we have to look at some other inverse functions and why the heck we need them.